Hey there everybody, in this video we're going to be graphing polynomials by hand using linear factors and zeros. So linear factors are when we break polynomials down into x plus something or x minus somethings. As we hopefully remember from Unit 3b, anytime you know a factor for a function, you also know a zero, aka an x-intercept. So what we're going to be doing is a whole bunch of factoring today with polynomials so that we can get x-intercepts, and we can use what we know from the previous lesson about the general shapes. That way we can sketch our graphs. We're also going to discuss something called the multiplicity, and that's just going to tell us how exactly an x-intercept behaves. So let's get to it. This is going to be a perfect spot to pause the video if you want to write stuff down. Also, as you're watching, if I'm talking too slow, click the little settings wheel and watch this at 1.25 or 1.5 speed. All right, so multiplicity. So the multiplicity of a zero or of a factor tells us if our x-intercept turns around or crosses. So I refer to this, instead of turns around, I say it bounces off the x-axis. So it hits the x-axis and turns around. So example right here. This is a perfect example of when it hits the x-axis and bounces off it. Or if it crosses the x-axis, I typically say through. It goes through the x-axis. So it starts on one side and then goes through it to the other. Here we have a bounce, here we go through. If you have an even multiplicity, so even multiplicity is when you have your factor x plus or x minus something. If you have, say, a squared attached to that, or maybe a fourth or a sixth or anything like that attached to that, you are going to bounce off the x-axis. So if it's an even multiplicity, it's going to bounce off. Most commonly, it's just going to be a factor squared. We very rarely see fourth, sixth, or eighth. An odd multiplicity, when we have ours factored, you could have x plus or x minus something to the first power, in which case that exponent wouldn't be written, or maybe x plus or x minus something to the third power. That's supposed to be a 3. So the exponent on the factor is going to be the multiplicity of the term. Now, some of you might be asking, why the ever-living h is it called multiplicity? Why did we not just call it the exponent? Well, the reason why it's called multiplicity, and I'm just going to make up an example, is if I had a polynomial that may be factored out into x minus 1 times x plus 2 squared and then x minus 3, this x plus 2 squared is really an x plus 2 times another x plus 2. So I can write this in kind of expanded form. So we call this multiplicity because it has been multiplied by itself 2 times. So it's kind of a double zero, and that's what creates a bounce, or if it was an odd, it would create a through point. All right, but I digress. All right, so here we've got examples in which we see graphs that have x-intercepts, and we can maybe determine the multiplicity of said graph. Okay? So what I'm doing is I'm just going through and I'm marking the x-intercepts. Now, as we know from previous lessons and units, x-intercepts indicate factors. So if I were to look at this first graph, I've got an x-intercept at -2. That means there's a factor of x plus 2. Right here, I've got a x-intercept at +1, so I'd have a factor of x minus 1. I'd have a factor of x minus 3. This is an example of what that polynomial might look like. Maybe there's a coefficient out front. Maybe there's not. I don't know. Don't really care. But I do know, since the right arrow is pointing upward, that the coefficient would have to be positive. I could look down here. I've got x-intercepts at -5, -3, 0, and 2. So I'm going to have factors of x plus 5, x plus 3, plain old x. You could write x minus 0, but just plain old x will do, and then x minus 2. So if I were to write this thing as factors, I'd have x plus 5. Holy cow, that's a terrible plus. X plus 3, plain old x, and x minus 2. Since right here we had a bounce point, right? It hit the x-axis and it turned around. That means this has an even multiplicity. So I need some sort of even exponent up here. I'm going to call that a 2. And the fact that this arrow is pointing down, it goes downward forever on the right-hand side, means I need some sort of a negative coefficient out front. So I'll just put a negative sign. Maybe it's negative 17. I don't know. I don't really care. All right, so that's what we're going to start seeing with the relationship. But what's going to happen is they're actually going to give us the factors, and we have to create the graph. So let's get to mathin'. We want to sketch the graph of this polynomial function. All right. First, leading coefficient. This thing is positive 2, and it's an odd degree. So it's a positive 2 with an odd degree. It's going to look something like that. Positive meaning the right arrow points up. Odd meaning the arrows do separate things. Now, we need to factor this. So I'm going to pull out a GCF first, 2x, and then I'd be left with x squared plus 5x plus 6. Almost entirely in factored form. So I've got 2x, and then, let's see, numbers that multiply to be 6 but add up to 5, 2 and 3. Anytime I see an x, that's going to correspond to an x-intercept. So I've written this thing in factored form, and that's going to give me x-intercepts on my graph. A plain old x, there's no plus, there's no minus sign. It's just 2 times x times this stuff. Plain old x indicates that we're going to have an x-intercept at 0. X plus 2 as a factor means that I've got an x-intercept at negative 2. Let's see if I can scooch that over a bit. Okay. And then x plus 3 means I'm going to have a factor at negative 3. So graphically, this is the outline of my function. So what I need to do is try to create a shape that looks like this, but goes through these points. So I'm going to go left to right here. I know that it's going to come from the bottom. I know it has to go through this point because it had an odd multiplicity. At some point, it's going to have to turn around because I need to hit this point here. And at some point, I got to turn around. So my graph should look something like this as I go through. I don't need to be super exact. I just need the basic shape. So it's going to go through that first x-intercept. Some point, it'll turn around. Some point turns around. So maybe something like that. Again, doesn't need to be exact, just a rough sketch. That's what this graph could look like. Let's see another one. We want to sketch the graph. We have negative 3 x to the third power plus 18x squared minus 27x. First and foremost, I'm noticing we have a negative lead coefficient with an odd degree. So negative lead coefficient means the right arrow is pointing down. Odd means the left arrow is pointing up. And in between, we have some sort of squiggly action. All right, let's factor. GCF first, negative 3x taken out of everything. So I'd be left with x squared minus 6x plus 9. If I continue to factor, I've got the negative 3 times x out front. Numbers that multiply to be positive 9 add up to negative 6. I'm getting negative 3 and negative 3. So this would be negative 3 times x minus 3. I can condense those and call that a squared. So now graphically, what's going to happen is I'll have an x-intercept at 0 and at negative 3. At 0, my graph is going to go through because that just had a multiplicity of a 1. And at 3, it's going to bounce off because I had a multiplicity of 2, an even multiplicity. So 0 and 3 are going to be my points on the x-axis. So let me get that marked off. So we've got 0 and 3. And I'm remembering with 3, I'm going to put a little star there. That was a bounce point, so I have to bounce off the x-axis. All right, so I need to fit this general shape and these 2 points. So it's going to start from up here. It'll come down. I have to go through that point as I come down. At some point, I got to turn around because I got to hit this guy. And it was a bounce point. So as soon as I hit this point, I'm going to turn around and go back down. So I'll start from up here, go through, bounce off, and then down here. Let's see if I can do that. So go through the first one, turn around, bounce off, go down forever. There we go. Your graph might not look the same as mine. As long as it's got that general shape, you're good. We don't really know how far down that little valley is going to go. We could figure it out by plugging in specific x values, but you know me, I'm a lazy man. Don't feel like doing that. All right, so here are the steps we've been doing if you need to pause to jot this down. We've started off by figuring out the end behavior, the basic shape. We then factored to find the zeros. We determined the multiplicity, so through point or bounce point at each 0, and again the zeros came from factoring. Now we can find the y-intercept. So the y-intercept is going to be when x is 0, what is the y value that pops up? And all that's going to do is it's going to give us an extra point to plot to shape our graphs. Now the y-intercept will always be the constant value, so the number chilling at the end that does not have an x attached to it. If every single term has an x, like this one, then your y-intercept will just be at 0. Because if I plugged in 0 for x, I get 0 minus 0 minus 0, still 0. All right, so let's get graphing. We have x to the third minus 2x squared minus 15x. Our leading coefficient is positive, so I know the right arrow is going up. The exponent is odd, so I'll have one of each type of arrow. In between, squigglies happen. Now we need to factor. Always start by taking a GCF out, in this case just a 1x. And I'm left with x squared minus 2x minus 15. We'll continue to factor. Numbers that multiply to be a negative 15 but add up to a negative 2. I'm getting x minus 5 and x plus 3. So now I've got 1, 2, 3 factors. That means I get 1, 2, 3 x-intercepts on the x-axis. I'm going to have x-intercepts at 0, at 5, and at negative 3. So at 0, at 5, and at negative 3. So 0, 1, 2, 3, 4, 5, and negative 3. All of these have a multiplicity of 1. So their exponents were all just 1, which means they're all odd multiplicities, so it's going to cross through at every single point. If there was an even exponent, then I'd have a bounce point. So I need to fit this general shape to go through these points here. So I know on the left side it's going to start pointing down. I need to go up, approach my first x-intercept, and I'm going to go through it. At some point I need to turn around, go through this guy. At some point turn around, go through that guy, and I'm done. Next problem. Negative 3x to the third plus 12x. The fact that this is a negative function means the right arrow is pointing down. I've got an odd degree, an odd exponent, so the arrows are doing opposite things. In between, curves happen. To factor, we pull out a GCF, negative 3x, and I'm left with x squared minus 4 on the inside. I continue to factor. You want to break this down into linear terms. Linear terms means no squared directly on the x. You can have a squared on the outside parentheses, but no squares directly on the x. So I've got negative 3. Hey, negative 3 times x times We've got difference of squares, which breaks down into conjugate pairs. So x plus 2 and x minus 2. So now I've got 1, 2, 3 factors, which means I'm going to have 1, 2, 3 x-intercepts at 0, at negative 2, and at positive 2. All of these factors have an exponent of 1. That's all odd, so they all have an odd multiplicity, which means it's going to go through all of those points. This negative 3, we no longer care about. That negative 3 just kind of gave us this general shape. So if it doesn't have an x, we don't care. All right, so let's get to plotting. We've got 0, negative 2, and positive 2. So 0, negative 2, and positive 2. And I need to throw this shape, oops, no sharp corners though, onto this graph. So I'll start pointing up on the left. I'll go through, turn around, go through, turn around, go through. There's my function. All right, next one. X to the fourth minus 2x cubed minus 8x squared. All right, let's see, we've got a positive function, even degree, so both arrows are going to be pointing up. In between, curves happen. We'll start off by factoring GCF x squared. Leaves me x squared minus 2x minus 8. We continue to factor. I'll get x minus 4 and x plus 2. I've now broken this thing down as far as I can. I mean, I guess if you really wanted to, you could argue x squared is x times this stuff. But now what I can do is start compiling my zeros. I'm going to have an x-intercept at 0, and that came from this right here. But that's going to be a bounce point because it has a multiplicity of 2. So that's going to be a bounce point. I'm going to have an x-intercept at positive 4, and I'm going to have an x-intercept at negative 2. So 0, 4, and negative 2 are going to be my x-intercepts. So let's plot those. We got 0, 4, and negative 2. And 0 was a bounce point. So I'm just going to make a little special note that I need to bounce off there. So I need to fit this shape, both arrows pointing up, to this graph. Well, let's go. On the left side, I know it's pointing up. At some point I have to go through my x-intercept. Somewhere I'll turn around and I have another x-intercept, but that's a bounce point, so I'll hit it and then I'll bounce off. At some point I'll turn around and go through this next one and finish out my graph. So that's an example of what this function might look like. All right, how many more we got? Holy smokes. We'll do number 6 and we'll call it a day. We'll do number 6 and call it a day. All right, so number 6 is already given to us in factored form. By the way, if you guys ever want to see the completed notes, they are available on our unit summary. I'm just thinking in the interest of time. All right, so I've got negative x to the third times x minus 3 times x plus 4 quantity squared. So this one's different because it's already factored for us, which, yay, that's awesome. So I can get my x-intercepts at 0, 3, and negative 4, so that's cool. But I don't know the general shape because I don't know the degree. Well, to find the degree, I could think, what would happen if I multiplied all this stuff together? Right? If I multiplied this stuff together, I've got 3x's up here. I've got an exponent of 1 right there, and then I've got an exponent of 2, because if I wrote this x plus 4 times itself by being squared, I'd have x times another x. So the overall degree of this thing, I'm essentially adding the exponents, is 3 plus 1 plus 2 is 6. And the fact that we have a negative out front means if I were to write this in standard form, I'd have a negative x to the 6th, blah, 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 plus stuff. Now, the reason why I want to do that is to get an idea what the general shape would look like. It's negative, so the right arrow points down. The degree is even, so both arrows do the same thing. In between curves happen. So when it's in factored form, they save us time because we can get the x-intercepts insanely quickly. But we do have to backtrack just a little bit to figure out what the degree of this thing was. And again, to find the degree, I just compiled all of those exponents. That's all we did. All right, let's get to graphing. Ooh, but wait, before we do, what's the behavior of these? Let's see, we have an odd degree, so that's going to go through. Odd degree is going to go through. Even degree, that's going to be a bounce point. So that's going to hit the x-axis and turn around. So I need to pay close attention to that one. All right, so 0, 3, and -4 with a bounce point. So 0, 3, and -4. And -4 is the bounce. All right, so I need to fit this shape onto this graph. Since it points down, I know it's going to start off being underneath the x-axis. It's going to start off being down here. So I approach my first x-intercept. It's a bounce point, so I'll hit it, and then I got to turn around. At some point, I got to turn around to get to this next x-intercept, and I'm going to go through it. At some point here, I need to turn around because I have another x-intercept to hit. So that's maybe what my graph looks like. For all I know, there might be like another squiggly down here. I don't know. Maybe, maybe not. But if it doesn't hit the x-axis, I really don't care about it. Okay, what I'm going to suggest you guys do is take a look at the completed notes PDF just to see what those graphs would look like if you need more explanations. You know the drill. If at any point you have a question, please let me know. And as always, folks, good luck, have fun, be safe, roll tide.